Okay. This slide tells you the definition of frequently used terms to describe the effectiveness of the antimicrobials. They are different levels. Number one, sterilization. Remember in the lab, when we using the loop under the fire, I say sterilization all the time. What does this mean? Curing everything, basically. Curing live body. That's called sterilization. The second terminology is called disinfection. This is basically, you are curing vegetative cell, but not in the spore, or may not be in the spore. Sterilization, a good example, autoclave. Okay, you do the flaming. That's an example. Disinfection, 75% alcohol. This is usually in the surgery room. Now, most of the time, when we talk about in the lab, I said every time you have to clean your bench. Over the weekend, you may clean your dorm. This is called sanitizing. Sanitizing is actually the lower level of the inactivation of bacteria. This is usually Q bacteria below regulation, federal or state regulation. Basically, around curing 3 to 5 log 10 CFU per ml bacteria. So said very simple. You're using chlorine water to clean your bench. Does not mean you cured everything. You may reduce the bacteria about 3 or 5 log, which means you can do a calculation. You are curing the bacteria 90%, 99%, or 99.9%. That is called sanitizing. It's the lowest level of curing bacteria. Okay, another one called antisepsis. This is disinfection of tissues. Patterns of microbial growth, death, they're not cured everything immediately. They're going to graduate cured. So I give you a very simple example. If I have a beef steaks, okay, I go ahead to cooking. Think about that where they kill bacteria first. On the surface. And the center is always delayed. Because the temperature not going to be increased immediately. It took time. So, what going to be the curve looks like? Let's say we are curing bacteria. It's not linear. It's very much like this. That's called a shoulder time. Like the lag phase, and this is going to be like a log phase, and they may have some bacteria still there. If you are cooking a beef steak to medium well done, 60 degrees Celsius will happen. The bacteria is still there. They could become resistant. And this is called tail effects. So just want to let you know, you're trying to destroy bacteria does not mean it's got linear, it's going to kill everything immediately. Okay, and also it's very interesting. There are some of the bacteria is viable but non-culturable, which means using traditional methods, you cannot cultivate them, but they still have a pathogenic information there. It cause a problem. This is what happened is people doing a server inactivation study and talk about in a different time using heat. And this creation two terminology, which is Z value and D value. So I have to turn this off. This is very interesting to terminology. What is D value? Time required to kill 90% of a target bacteria in a specific food product. What means 90%? I have 1,000 cells. After heating, I left 100 cells. That's called you killing 90%. Okay, if I do a log 10, what it becomes? This 3 log and this is 2 log. So this equals 1 log reduction. That's called D value. Okay, what is Z value? Z value is a little bit different, but related temperature change for changing 1 log or 90% of D value. And that is called Z value. These two are very important thermodynamic index to talk about the thermal inactivation. And this brings another whole topic called predictive microbial mathematician. It's a different discipline. Here we have a different available commercial model. Software could do the analysis. And sometimes with the chemical signals, it could be combined with the AI technology, machine learning, all those things, fashion stuff that comes out. So just want to let you know, thermal inactivation is not that simple. There's a lot of story behind that. Just give you an example. Next, we want to talk about the conditions enforcing the effectiveness of the antimicrobial agent. This is easy to understand. Population size, of course, large population take a longer time to kill compared to smaller population. Population composition, well, of course, it's only individual bacteria combined to your multiple species. The multiple species is difficult to kill. So give you an example. If I have only E. coli grow on the bench surface, I use 100 parts per million chlorine, I can clean them. If I have somehow have E. coli with Pseudomonas, Pseudomonas is a sporage bacteria, then it will be very easy to generate a matrix we call biofilm. Then you may need 500 parts per million, or maybe 1,000 parts per million of chlorine to inactivate them. The next one is the concentration. Usually higher concentration, more effectiveness, does not mean it's linear. This is happening lots of the times. So one time we're using peroxyacetic acids in a squash processing plants. It does not mean you're using higher concentration it's effective. Sometimes it's similar. Exposure time. Basically longer exposure time, the more organism is killed. Temperature, high temperature usually increasing killing. But sometimes you cannot use it. So for example, chlorine water. You cannot use hot water. They will generate off gas. So just want to mention, okay? Not local environment. We know acid environments, viscosity, organic matter. This when we talk about the chlorine solution in our exam 4, we will mention about organic matter is very important. So give you a very example. This is happening during the COVID-19 time, and the people have to do cleaning and sanitizing of your dorm. And I have told all my students, the first thing, your dorm has to be neat and tidy. If you have all the dust left food, all the trash everywhere, you spray chlorine water or sanitizer, it's not effective. Because those, we call it's a soil. Quotation mark soil. It's an organic chemical matter will distract or break down the effectiveness of most of the antimicrobials. So I said, when you do sanitizing, make sure your house is cleaned already. Make sure it's neat and tidy. So very simple. We just mentioned if organisms in biofilms, they are less susceptible to many antimicrobial agents. So that's a conditions that affect the antimicrobial to killing or inhibit the bacteria. Some examples, this is we know. Physical control methods, temperature. Because water is removed, floating nuclear gases are destroyed. This is what we do in the lab all the time. And this is not a good picture. You have to sterilize the whole loop. Is that right? Not on the top. Dry and heat moisture. Heat. That is important. And I'll give you an example. 72 degrees Celsius, curing bacteria in 15 seconds in flashing pasteurization. This is lots of the time we do for the milk products. If you buy a bottle of the milk from Google, you look at the label, they say flash pasteurization. This means 71.6 degrees Celsius, 15 seconds. So that's a reason. Can you put the milk in the refrigerator for a week or 2 weeks or a year? Of course it will be spoiled because they are only killing background flora and a certain pathogen. And if you look at that, home freeze temperature minus 10 degrees Celsius. Now, home freezer temperature, this is another issue regarding for the quality. Because if you put a beef into the home freezing, a refrigerator, what happened? 3 months later, you took it out, it's not going to looking good. Because low temperature, relatively low temperature, -5, -10 degrees Celsius, very easy to generate the crystal, the ice crystal. And the ice crystal will damage the structure. So, what's the effective way to do? Flashing pasteurization. Instead of you generate the crystal, you generate nuclear. So that's something we talk about in my other class, which is for the chemistry, we talk about that. Refrigerator temperature 5 degrees Celsius. Well, not lots of people do that. Lots of people do 7, 10. Human body temperature 37 degrees Celsius. Low up that is not good for fever because the enzyme of your body doesn't work. So you go up, you see spoiled. Spores usually will be killed 2 hours in boiling water. And the boiling temperature 100 degrees Celsius not always happened because it's related to the elevation. So West Virginia, 94 degrees Celsius, 94, 95, we're in Appalachian Mountain. In Rocky Mountain, which is Colorado, where I got my PhD, maybe 91 degrees Celsius. And you go to the Emirates, maybe 70 degrees Celsius. The egg could be boiled. So that's something I want to talk. 121 degrees Celsius, 15 seconds. No, 15 minutes. This is autoclave conditions. Okay, 140 degrees Celsius. Well, pathogen can kill in 3 seconds. That's ultra high temperature processing. We have a certain tool developed by food engineering. They could have a beef steak go there like 1 second, and they could be used. So there are some studies are doing about that. Spoiled have to be killed in hot oven 160 degrees Celsius. But you always remember, what is the dangerous temperature zone? Do not forget about this guy. 40 to 140 degrees Fahrenheit. This is when we talk about the Clostridium perfringens. We mentioned this guy is very interesting topic about that. Okay, pasteurization, created by Louis Pasteur. Only killing background flora and certain bacteria, not killing everything. So pasteurize of the milk. Steam sterilization, we talk about in the lab all the time, it's called autoclave. It's a sterilization process. You kill everything. So how we make sure the autoclave is working? We're using geobacillus, because geobacillus is a hyperthermophile. If the geobacillus is still survive, we will say that autoclave it doesn't work. If geobacillus is killed, we will say the autoclave works fine. It's a QC, quality control species. It's a geobacillus. Radiation. Yeah, we use radiation, X-rays, gamma rays. So what's the mechanism behind? Everybody knows the TT will be combined, called cyanodiamide. But they could be recovered. And I also want to say the sunlight is also a kind of natural antimicrobials from the radiation. So we have some products generate using radiation, have vegetables, strawberries, but we have the concern is the safety. How many residue radiations chemical going to be there? So people may be scared about that, but it is used a lot. We mentioned about the E. coli in the ground beef and the beef products. In the United States, the E. coli 0157H7 is zero tolerance. So for the ground beef, you cannot cook it, you cannot spray antimicrobials. So before they go to the market, what they do? They go through radiation. So that's the last defense system for them. Okay. Next one, chemical control. This is the slides which is a talk about what is the ideal antimicrobial chemicals. They can able to kill slow bacterial growth, non-toxic to the human being, soluble in the water, have a longer shelf life, effective at lower concentration, as low as possible, and depends on the temperature, pH, and we call it external factors. You choose certain antimicrobial chemicals. But there is no ideal chemical can fit all these categories. In the real life, we have food soil. We have fat from the food, protein, sugar, carbohydrates, and the mineral salts everywhere. So we have to do a sanitizing. So what we do? We're using detergent, soap-like. Most of the time we have surfactants. We call it emulsification. We break down the large item to smaller one. We put a builder there. So different type of the detergents will generate. This could be alkaline, could be acid, it could have enzyme, or have oxidizing agents. And we want them to be safe to use. So most of the time they are solutions. They are hydrophilic, easily dissolved in the water. And we also make the salts. They can be easily dissolved in the water. Because there are some chemicals. Let's say we mentioned about antimicrobials, antibiotics. Lots of them are not easily dissolved in the water. They are hydrophobic. If you prepare, you have to use alcohol. Okay, so that's something I want to let you know. So detergents, how they're working, physical interaction with food and the chemical interaction, they basically combine together. Something we use a lot, benzoyl chloride, ammonia ion, contrary ammonia compounds, cause the leakage of the cell membrane system, cetylpyridine chloride. The right one here is CPC. This guy, I did this research a long time ago. It's like a soap. It's bubbling. This is the most effective antimicrobials used in the chicken chilling process. It's really interesting about that guy. People trying to use this on the squash surfaces and also on the cantaloupe surfaces. I see some of the study about that. So we have our chemicals, we have our sanitizers, we need a regulation. What are the regulation? In the United States, 3 agencies for regulation. Number 1, Environmental Protection Agency, EPA. We need to make sure they are environmental friendly, no toxication material generated. If they want to use on the food products, what we need to be approved is by FDA, Food and Drug Administration, and the USDA, the Department of Agriculture, Food Safety and Inspection Service. They need to make sure they are approved by the EPA, registered, and can be used on the food contact surfaces. So, not on the sanitizers can use on the food contact surfaces. Only certain things we can use. This is 1996. FDA approved the chemical sanitizer used on the food contact surfaces. Chlorine. We will talk about the chlorine later on more detail. Chlorine very effective. Can kill bacteria in 5 seconds. The allowed concentration 200 parts per million. But they will generate byproducts. Chlorine dioxide, it's a gas, difficult to control. Idophones, long time ago people use it, but find it's very corrosive. But people, why they use it? Because there's a color. What's a good thing for there is a color? You know you did it. It's very good for verification and validation. Contrary ammonium compounds, we call it a COTS. That's used basically is on the benchtop. All the labs they do. Acid, carboxy acid sanitizers, they're usually low pH. Let's say citric acid, lactic acid. Most of them coming from cherry originally, and they are usually originally effective for fungi. But later on people find that effectively using in the bacteria. But you have to make sure the pH is within their acceptable zone, effective zone. We call it a pKa value, and we're going to talk about later in exam 4. The last one is I'm doing in the lab a lot, is hydrogen peroxide and peroxyacetic acids. Basically, they're going through oxidizing process, they're going to killing the bacteria. And they're the combined products from that, we call it samidate. This is what we did in West Virginia for the small farm in this area for the fresh produce growers. So that's a sanitizer. Just give you an introduction. Some of them we'll talk more detail in the exams in the exam 4, where we talk about antimicrobial application. Some examples. Not going to go there all detail. Phenolics. This is the old first antimicrobials we used. Very effective. It's corrosive. But we use it because there's a color. We know we used it. Alcohol. There's one thing I want to mention. Pure alcohol, 100% alcohol, there's no effective for killing bacteria. Alcohol must dissolve in water. So what in the lab we are using? 95% alcohol. Clinically in the hospital, what they're using 70% alcohol. Never use pure alcohol. It's not effective. When I was working in the company, we have the electron microscope. We see the bacteria reacted with alcohol. It's kind of interesting. They're just tumbling, like dancing, and not even do anything. Two chemical items of alcohol is ethanol and isopropanol. Contrary ammonium compounds. This is one we use a lot. Cetropyridine benzalkonium. Aldehyde. Formaldehyde, what are they used for? This is not used for food products. This is used for preserve animal tissue. So where you see these things? In the museum, you will see that. You have like 100 years old, 1,000 years old, like some dragons or some weird stuff. They have to preserve it. I just make a joke. They use formaldehyde. So animal tissue preservation, not used on the food products. Okay, we're using lots of the antimicrobials. People are smart. Some of them are approved, some of them not approved. We have some natural control products. Okay, we can use bacteriophage. It's a virus to kill bacteria. We can using bactericide. Where the bactericide come from? Lactic acid bacteria will secrete those chemicals. So just want to let you know, the biological control, there's lots of things. There's a plant-based antimicrobials. We call it essential oil. But what's the hurdles to use those is the smelling, the flavor. They're going to add flavor to the food products. And also the price, because it is expensive sometimes. Okay? So this section is very general, very simple, just give you conclusion of the microbial control. So we'll have a review on Tuesday.